So now let's look at some practice problems where we're going to set up some models for differential equations. So the first one is just going to look at some graphs of functions and think about how these relate to different ideas, right? We're thinking about modeling these real life ideas with functions, with derivatives given by these graphs. So we have four things here: the temperature of a piece of steel heated in a furnace and left outside to cool, the speed of a constantly decelerating car, the amount of money in an interest-bearing bank account into which $83 is deposited, and the temperature of a glass of ice water left on the kitchen table. Note that some of these things correspond to derivatives, and some of these things correspond to the just the original function. But let's just try to match these up, and let's try to talk about them. First, we have that we have two of these functions are increasing. This is increasing, this one is increasing, and two of them are decreasing. So let's just try to match it up, which one's increasing, which one's decreasing. The temperature of a piece of steel heated in a furnace and left outside to cool, that temperature is decreasing as it is cooling. And the speed of a decelerating car is also decreasing. If we put money in an interest-bearing bank account, that is going to be increasing the amount of money that we have. And the temperature of a glass of ice water left on the kitchen table will be increasing as it's going to approach the value of the temperature that's outside or that's in the room. So we can kind of already match a couple of these together. Let's think about what's going on. If we have a piece of steel heated in a furnace left outside to cool, it's going to quickly decrease, and then it's going to level out and approach room temperature, or wherever it is going to approach some cooling level, right? And that's going to be this first one, part A. The other decreasing one is this B here, and that's going to be that we start at some speed, and if we're decelerating, we're going down at a constant rate. The speed is going down at a constant rate. The actual speed itself would look different than this. And note that this is the graph of the derivative. Right? And this function, this derivative, right, might be that speed at this point is equal to maybe something like negative x plus 60, like 60 miles per hour, and we're decreasing the whole time. That's the equation associated with that graph. I'm making up these values just to kind of fit that graph, but maybe something like that, where we have a y-intercept of 60 and a slope of maybe -1. So this would be a differential equation before we move on to the other things. This is a differential equation that will model the behavior of the speed that we're going on. Speed is representative of a derivative in this case. The other two are increasing. They're doing so in different kinds of ways. So the amount of money in an interest-bearing account, that's just going to keep on getting bigger and bigger and bigger. That's going to be part C. Right? This is going to be some exponential equation. Similar to this is an exponential decline. And this last one here is going to be part D, and this is going to be exponential as well. It's more like logarithmic. It's going to be that temperature is going to approach some temperature that's going to be room temperature in some way. All right, so this example is here to just show us how to think about functions, what's going to be important. Noticing when we have decreasing or increasing functions is going to be very important. We're thinking about derivatives. That's the whole point of differential equations, how they're changing. We're going to see a lot of exponential equations, right? Everything with exponential is going to have to deal with a rate proportional to something. We're also going to have to deal with linear things like this speed. And we can think about speed as a derivative itself. We can think about differential equations in that light. All All right, so let's take everything we've learned in the first part of this video, and let's actually model some real life behaviors. These problems are going to be fairly quick, but we're going to do a couple, and then we're going to use all that information to start section 9.2. We can really start diving into what differential equations are and how to find solutions to those equations. So this first section 9.1 is more of a warm-up to what we're doing. All right, so here we go. Here's our problem. Let's find a model for what we're dealing with here. A bank account that initially contains $25,000 at the beginning earns interest at a continuous rate of 7% per year. Withdrawals are taken out at a constant rate of $4,000 per year. Write a differential equation for the balance B in the account as a function of the number of years T. So real quick, what we are looking for is the derivative of B with respect to T. We're not going to write down what is B equal to. We can do that later on in this chapter, but not right now. We're looking for dB dt. And one kind of red herring here is this $25,000. All right, the $25,000 does not influence the derivative at all. That's just how much money is in the account at the beginning. All right, that's not going to have anything to do with how it's changing every single time. What we're going to do is think about instead this earns interest at a continuous rate of 7% per year. So this 7% interest rate is going to be our proportional growth. This is our idea of growing at a rate proportional to something. We earn 7% each year. If we have a little amount of money, that's going to gain just a little bit amount of money back. If you have a savings account, you know that if you have a little bit amount of money in there, it looks like your savings account's not really gaining much. But if you have a lot of money, that 7% will gain you a lot of money in that account. So that is proportional growth. And we know how to do that now. That's going to take the rate. We're going to write that always in decimal form. 0.07 times how much money is in the account, is that's what matters, is how much money is in that account. So 0.07B. And then we also have a third piece of the puzzle, and that is this withdrawals taken out $4,000 per year. So that's going to be each year, no matter what, we're going to decrease the amount by 4,000. It doesn't depend on how much money is in the account at any time. That's just going to be a minus 4,000 each time. That's very similar to our allowance example in the first video. So here we're kind of combining the two different sorts of growth and decline that we're going to look in this chapter or in this section. Proportional growth, and then in this case, just a constant decline. And this represents the differential equation. So again, that $25,000 does not play any role in the actual derivative. That would actually correspond to if we wanted to find what is B equal to, we would probably have something like 25,000 plus something going on there. And actually it wouldn't be a plus, but it would be times something. So that has a role to play in the original function B, but nothing with the derivative itself. All right, one more problem. This one's going to be a little more complicated. We're going to try to show complicated problems so we can deal with easier ones in the worksheet. A country's infrastructure is its transportation and communication systems, power plants, and other public institutions. The SOLO model asserts that the value of national infrastructure K increases due to investment and decreases due to capital depreciation. We'll go back through all this after we read it. The rate of increase due to investment is proportional to national income. We're going to call that national income Y. So we're going to assume that K1 is going to be the constant of proportionality. The rate of decrease due to depreciation is proportional to the value of existing infrastructure. That's going to be K. And we're going to assume K2 is greater than 0. So we're going to try to put all this together into a differential equation for K. We're going to be looking for the derivative of K with respect to, in this case, investment Y. That's our other variable that we are looking here, Y. You may think that the variable should be T, but we're kind of given in this first little thing that K increases due to investment, right? And that investment depends on the national income, which is Y. So it is changing in terms of Y. All right, so the two parts here is we have the rate of increase due to investment is proportional to national income Y. So there is our proportional to Y, right? We're going to multiply something by Y, and that constant we're going to multiply by is K1, whatever that rate is, so K1Y. The other one here, the rate of decrease due to depreciation is proportional to the value of existing infrastructure, that is K. So we're going to have here times K, and that's going to be times K2. And we're going to combine those, and this way we would just add, but since we have a decrease in the second part, then we need to subtract the second part. As we're saying, K2 is positive. We'll make a little note at the bottom that if K2 were negative, then we would have K1Y plus K2K, but that K2 would be negative, so we can think about it as subtracting a positive as well. So a couple things to think about in this problem. Note that we're done. This is the differential equation. This models the behavior. We're not going to find what K1 and K2 are, but we can see that in our differential equation, we have our variable Y. We're kind of used to that being the case. But we also have, right, our K here in the actual expression itself. And we're going to constantly mix in our differential equation. We're going to have our function Y and our variable X or T in there. And we'll see a bunch of examples of that in the next section. So once again, section 9.1 is an introduction to these ideas. We're going to do some simple kind of problems like we've done in this video to prepare for the next sections and introducing more complicated things for differential equations.